Hello dear students. Today in this class we will discuss about the new topic, that is oscillation of a liquid in U2 test. So oscillation of a liquid in U tube formators. So until then we have discussed the oscillation of a particle, oscillation executing the simple harmonic motion, its kinetic energy, acceleration, velocity. These all things we have already discussed. Now we have to cross check with the help of the liquid in the different shape. So whether that particle or that liquid itself will behave like a simple harmonic motion or what. So in SHM it is. So simple harmonic motion it is. So let us take a one U-shaped tube here. So I will just draw it like a U-shaped. It should look like a U-shaped tube it is. Right? So in that U-shaped liquid tube, I will enter certain water here. So these are the two limbs I can say, where two ends are open here, filled with the liquid. Either liquid may, you can take a water also, or a different density of a liquid. So you can take it here. So these two are the limbs here, right? So now if you fill the water here in this part, right? Now it is with respect to the other limbs here, it is a raised certain height here. I mean the total height of the tube, you can cross check here. This is the height I'm going to tell. This is the part where I can just take this part. Like this is what we can say, it is a depressed in the sense what, displaced. So it is a certain distance, it is a displaced, like the liquid. Consider the liquid of a density rho here in the U-shaped tube of a cross-section area A. It is cross-section area A, and rho is the density of the liquid up to the certain height h in each limb in an equilibrium position. So each limb is there. No, this is nothing but the equilibrium position where the liquid behaves as or experiences the simple harmonic motion, or in equilibrium position also we can say that it is a mean position also. Equilibrium position means mean position also in two limbs. So through the displacement x, so I can say no, through the displacement x. So once it is taking the displacement here in the limb here, it rises up the same amount in the other limb. So it is going to rises up here same amount in the other limb. So this is the another limb, same part it is moving up here. That means the difference between the liquid level in the two limbs is said to be as a 2x it is. So difference between the two limbs, water rised in that is of 2x. Then depressed liquid left, depressed liquid is there, no? If you left it freely, so it's going to be experiences that moving up and down here. So when you leave it freely, once it is depressed, means as in case of spring, we'll do know what we are doing here. If the body is there, so just displaced a certain distance here. After that, if you released it, it's coming back to its original position. Similarly, here also, what will happen once the liquid is there in the U-shaped tube? That tube has a consisting of liquid. Once it is depressed here, right? So it is rising up the same amount in the another limb here. Differences between is 2x I said. Then once it is depressed and released it starts to experiences the moving levels of the liquid in the two limbs oscillates like a up and down as a simple harmonic or simple harmonically about time It's a equilibrium position. When this part is equilibrium position for this limb, this part is equilibrium positions for the second limb. So they will act as a moving up and down here. So now that mass of the liquid in the U tube, then mass of the liquid in the U tube is equal to the, what is that, volume of the liquid and density of the liquid here, where mass is equal to 2HA into rho it is. Means what is here, mass is mass of the liquid is equal to 2H means what here, total distance, cross sectional area and the density of the rho here. So volume is what, 2HA, density is a of a liquid it is. So height of the liquid 2x provides the restoring force it is. That means this position is there, no distance between the two limbs, 2x produces the restoring force, means it's going up and down, which is going up in the sense what, it is a disturbed position of the mean position. So once it is released, it's trying to coming back to down, means it experiences the restoring force. So restoring force is what, opposite to the direction of displacement, that we know. What is that? Weight that experiences the restoring force here, 2xg. What is that? Weight of the body in the 2x position. So it is what it is experiencing here, weight of the 2xg, it is that to downward, 2xg, it is a downward here, and once it is moving up, no, that is also 2xg here, minus direction. So moving upward means minus 2xg upward direction here. So the weight of the liquid 2x experiences the restoring force, that I can say F is equal to, so F is equal to minus 2x cross sectional area A and the rho density, and this is a G. 2x area is also considered here and the G is there. The density of liquid is also important. So negative sign indicates what here? The force and the displacement are opposite in direction. So opposite in direction, that we know why the negative sign comes here, opposite in direction. How it is? So body is a moving upward direction, but the force which is experienced by the liquid in the U tube experiences the downward in the sense what, it's moving towards the mean position. So force is there downward, moving towards the mean position, displacement is upward. So that's why negative sign comes here, right? Next part, it is in the simple harmonic motion. So simple harmonic motion, what will be the force? So I will write it here. So F is equal to minus kx. So this is the simple harmonic motion force it is. So once you compare with these two forces here, so what you are getting, we have to compare just, I'll just erase this one. We need to compare the force of the limbs, liquidized, that is F is equal to minus 2xa rho g it is, in simple harmonics minus kx it is. So what is comparing these two forces, because in U tube it experiences the simple harmonic motion, we said here, that is of kx is equal to 2xa rho g it is, rho g it is. So x cancels, it remains with k is equal to 2a rho of g here. So time period of oscillation, time period of oscillation of a simple harmonic motion, if particle is executing, that is of t is equal to 2 pi root of m by k it is. So in place of k, I'm going to substitute here the K value what we have got just now. So here what is the value of K? What is the meaning of K here? That is the force constant in the of the liquid in a tube here. So that is what 2 T is equal to 2 pi root of M by K it is. So M value, mass of it is what? 2 pi. Mass of the liquid is what here? It is just now written, no? 2HA into rho. K is what here? 2A rho of G. So what all get cancels? 2 A rho get cancels, remains with the 2 pi root of rho by root of H by G it is. So root of H by G. So that means it experiences the simple harmonic motion because it follows the whatever the function it is executing the particle in the simple harmonic motion. So this is about the oscillation of a liquid in a U-tube shape, simple harmonic motion. So in the next, after this part, we are going to discuss about the oscillation of a floating body. So oscillation of a floating body. So let us consider the one wooden cylinder here. So let us consider the oscillation of a floating body in a simple harmonic motion. So consider the wooden cylinder of a mass m here. Its mass is m here. This is of a wooden cylinder. I have just drawn the diagram. And density of sigma here, the cross-sectional area A, right? It is filled up with some liquid here, right? Completely it is filled up with a liquid. In that liquid, we have just depressed, introduced the, we can say the cylinder, wooden cylinder here, depressed through the displacement of certain wire. So this is the equilibrium position when it is inserted in a container of content of liquid here, right? The mass of the wooden block is m, density of the wooden block is sigma, the cross sectional area A it is. So cross sectional area A it is, and height h floating in the liquid of the density rho. So this is a certain height it is experiences, that it is not needed. This is the density of the liquid it is. When cylinder is depressed through the displacement y. So once it is introduced, this is the equilibrium position. Depressed means just pressed. So it is moving a certain distance y here. So displacement, this part will say it as this is a displacement it is, because we have just pressed the wooden cylinder here from the mean position. It is. Then it is released. So it oscillates up and down simple harmonically about an equilibrium position. So once it is pressed here certain distance, it is changed, means displaced from the equilibrium position, and it starts moving up and down, means it experiences the simple harmonical in the form of not in this horizontal, it is moving in the up and down format it is, right? So but this is balancing by its own weight, that is of mg here, right? And this displaced part, its balancing is ah sigma and g here. Y means cross sectional area, certain height, and sigma is a density of the cylinder here, and g is a acceleration due to gravity. Then weight of the cylinder is equal to weight of the liquid displaced. So why I have maintained here, weight of the cylinder body should be equal to the weight of the liquid in the liquid which is made that cylinder to be depressed. So I can write it here, weight of the body is equal to weight of the liquid in the which is responsible the wooden block to get displaced of a certain distance here, that is of ah sigma g it is. So g cancels, remains with m is equal to ah sigma here. So this is the mass of weight of the cylinder tells. When cylinder pushed down by a y distance below in its equilibrium position, the upthrust provides us the restoring force it is. Upthrust means in the sense what it is. Once it is displaced and released it. Same things what we have discussed in the YouTube here. The same thing it is happening. The liquid, this wooden block, it's just displaced downward, but it want to come to its original position. That means this part is, which is a cylinder pushed down by certain distance in its equilibrium position, the upthrusts, which is moving upward direction, provides the simple harmonic motion. Means in the sense of restoring force. So restoring force is opposite to the direction of displacement. Body is moving in this direction, force is there in this direction, moving back to its original position. The upthrust is an upthrust experiences the restoring force. That upthrust is equal to the weight of the displaced liquid. So weight of the displaced liquid here. So F is equal to, I can say, minus AH rho G it is. Minus it is not H, it is displaced from AY rho G it is. Y it is. Y is the displaced one. A is the area of cross section. Rho is the density of the liquid. And G is the acceleration due to gravity. You know that negative sign indicates forces and displacement is opposite in direction. But in simple harmonic motion, force we know that minus ky. Here I am taking minus ky because the distance we have measured it as a notation, we have taken it as a y here. You should not get confused. So both you can compare, you will get that what is formed here. Ky is equal to ay rho g here. So y get cancels, remains with k is equal to a rho g here. So that is of a rho g. Then time period we have in a simple harmonic motion, that is of 2 pi root of m by k it is. So mass is what here? Mass of the wooden block. We got it here, ah sigma, right? And k value we have got it here, a rho g it is. So what all get cancels here? A get cancels, remains with the 2 pi root of h sigma rho g it is. So this is what time period of a body, wooden block or wooden cylinder, when it is in the form of floating body. The floating body is also experiences this simple harmonically up and down. That means it experiences the simple harmonic motion. When you go ahead with the frequency here, so frequency part, so that is what? Reverse part of the time period. You can go ahead with the reverse part of the time period, that is of 1 by 2 pi root of sigma g by h into sigma. So this part we can say that same function what the body executing the to and fro motion, the same thing it is experiences the simply harmonical motion when body is floating. That also experiences the upthrust and the down, just because of restoring force is developed. So that experiences the we can say floating body is also experiences the simple harmonical motion. So next, a very important part, it is oscillation of a ball in the neck of an air chamber. So we are taking one ball and we are allowing that to fall through in the neck of air chamber. So we have to consider one air chamber. We have to allow the ball to be enter into that neck of the air column. So that ball is also experiences the simple harmonic motion or not, that we are going to study here. So now let us take the oscillation of a ball in the neck of the air chamber here. I have drawn the diagram here, right? So air chamber of a volume V. So air chamber we have taken the certain volume V here, provided with the neck of a cross section area A it is. So cross section area of a neck it is. So we should write it here, cross section area of neck it is A, into which the ball of the mass M. So mass of the ball is M here. This is the ball, right? So it is has to be enter into this air chamber. Before air chamber, it has to pass through the neck of the air chamber here. When mass can move without any friction, means ball should pass through this neck portion of the air chamber, but in that passing through the position, friction should not be there. Friction is what? Opposing force which is a development. That friction is not there. Obviously without friction it will pass through. When ball is pushed down, when ball is pushed down here, means from the neck it has to pushing down. So certain hope to be this is a equilibrium position. Once it is pushed down, so it is displaced a certain distance, y here, small displacement we can say, and after pushing here, if you just release it, there only it will experiences the up and down motion it is. That means up and down simply harmonically about its equilibrium position also we can say. So it is moving there only up down. So certain time period it will feel it as, or it experiences as a restoring force, and the experience is up and down in that in the equilibrium position it is after pushed, after displaced certain small displacement. If ball is pushed down through the small displacement y here, then volume of the air chamber decreases. How? Means when ball air chamber is there, in that air will be there. So if you just push that ball, air chambers or air in that chamber get disturbs, means volume of that air is getting decreases here by the, or else we can see the change of the volume. So delta V. So these things we have already discussed in the volumetric strain, hydraulic stress. These all things will come into the this part of the this part of this ball experiences here, right? So that volume is decreases as a V2 delta V. It means change in the volume also we can see, change in the volume, or volume decreases here. So volume decreases, right? Now volume of volumetric strain we can say it is. So volumetric, why we are saying it is volumetric strain? Because when the body is enter into the air chamber, so it experiences a small displacement. Once it is entered, displays a certain distance, then air in that air chamber, its volume is going to be decreases. So that situation we'll call it as it is a volumetric strain. So that is nothing but the change in the volume by the original volumeters. So change in the volume and the original volume. So delta V is what here? Change in the volume in the air chamber. V is the original volume of the chamber here. Now in this next part, after getting the changes in the volume of the air chamber, when pressure is applied, so when pressure is applied, when pressure will be applied to the ball here, so that time hydrostatic stress is produced. Pressure means what? Force by area. So we are just pushing, or we are allowing the body or a ball to be depressed in the sense it is displaced from its equilibrium position. It has to pass through the neck portion of the air chamber to enter the air chamber, right? So there where pressure is applied to push the ball, so that time hydrostatic stress is produced. Hydrostatic stress is produced. Stress and strain, already you have learned it, right? So produced due to the passing down the ball becomes equal to the pressure. So this passing through that down, no, pushing that, the pressure is developed. So bulk modulus of elasticity. So that is of, we can say that bulk modulus of, so again I'm not discuss this bulk modulus, this already you know it. So bulk modulus of elasticity, why it is getting bulk modulus of elasticity? It is due to the force, that is restoring force is developed when ball is stretched down. It is passing through the air chamber here, right? Next, when pressing the ball means automatically pressure is developed. So pressure is what? Force by area. So bulk modulus of elasticity develops here. That is hydrostatic stress and volumetric strain. So this is nothing but the ratio of hydrostatic stress and the strain. That is nothing but the stress and strain. Modulus, bulk modulus it is. So we are getting E is equal to, what is this? E is nothing but the elasticity, bulk elasticity. That is nothing but the pressure divided by change in the volume by the original volume. Or else we can say that P is equal to minus E delta V by V it is. Right, this is of pressure. What pressure is developed in the air chamber where we are passing the ball through the neck portion of air chamber it is. So this part we have got it here, right? So that is of P is equal to minus E delta V by V it is, right? So next part we are getting, what is that? I'll just erase this part. So up to this we have got here, right? P is equal to minus E delta V by V it is. Now pressure we have P is equal to F by A it is. So F by A. So F by A we can write it in the form of minus E delta V by V it is, where F is equal to minus E, as we said delta V is equal to, this was not mentioned no here. So delta V is equal to what here? Area of cross section and a displaced form of ball. So AY it is, I'm just substituting AY volume here. So original volume will be remains as a V only here. So this part, sorry, this is A, that means minus E A square Y by V it is. But force in the simple harmonic motion, what is that? Minus Ky here. So compare these two. Ky is equal to Ea square Y by V it is. So y get cancels, remains with the K is equal to Ea square by V it is. Ea square by V it is. Then time period of the simple harmonic motion. So time period of a simple harmonic motion, what is that? So T is equal to 2 pi root of n by k it is. So 2 pi mass of the, so mass of the ball, ball. So mv, m is there as usual, k is what here? Ea square into v. So this is the time period. If you go ahead with the frequency also, that is nothing but the 1 by t here. So 1 by 2 pi root of Ea square by mv it is. So this is about the frequency of the body which experiences the simple harmonic motion even in the, when it is passing through the we can say passing through the neck portion of the air chamber here, that is also experiences the simple harmonic motion here. So until then we have discussed oscillation of a body in a floating form, also oscillation of a liquid in the U-tube shape here, and the oscillation of a ball in the neck portion of the air chamber, or different kind, wherever we can take a many kind of examples. When the body will experiences a displaced from its equilibrium position, so once it's try to come back to its original position, due to the restore force is developed, so that restore force will make the body to execute the simple harmonical motion, or else we can say that it experiences the simply harmonic equilibrium position. So body will move towards the up upward direction and the downward direction, and to and fro motions, and body itself is floating in the sense of moving up thrust and the down. So these all are experiencing the simply harmonically, I mean simple harmonically uh, oscillation or a motion. So that kind of bodies experiences a simple harmonic motion. If you compare with the already particle executing the simple harmonical motion, to and fro motion, that force we have already known it as F is equal to minus kx, where k is a constant, the force which is acting on the particle here, where x is a displacement here, right? So wherever you can taking the particle, that force will call it as it is a force constant. In the previous case we have taken the spring here, so where we have taken a k it is, so that is called as the spring constants. Here we are taking k as a constant which is experiencing on the body here, that experiences the simple harmonic motion. So these are the very important concept. Based on this we'll have a plenty of numerical problems also. But the thing that wherever whichever body they had given, so they will experiences the simple harmonic motion or not, we have to cross check with the functions we have already discussed. That is x is equal to a sine omega t here, or cos omega t, right? So plus or minus acceleration, velocity, so these all things is experiencing, even though these are not following, those particles also experiences a simple harmonic motion. So what are those, that also we have already discussed. So this comes here almost end portion of this chapter, and the last part it is damped oscillations are there, free oscillations are there, and forced oscillations are there, that we are going to discuss in the next class.